in terms of the talk, we're going to start with just an intuitive overview of general machine learning. So I assume that most people here will have at least an intuitive understanding, so we're going to go through that fast. Then we're going to try to build a single set of kind of like machine learning and heavier deep learning models. Then we're going to jump into building a distributed architecture, and then understanding how we can scale it up. And this is just a big picture. I only have 30 minutes, so I won't really have time to go into much detail. I would have loved to just be able to jump on code and show stuff around. And today, what we're going to do is I wanted to push through learn by example. And what better way than to just build a tech startup today? And we're going to hop on the hype train of cryptocurrencies. So imagine we are this bunch of people in a garage. We're going to build this startup called Crypto ML. We're basically in September last year. We're about to jump into the crypto craze, and we want to build something that can predict the crypto craze and can also sustain it and survive it. Right, so I found this data set. It has like top 100 cryptocurrencies. Data goes back all the way from the beginning to last year, September, which, it's actually September, but that was, if you remember, when it all, went downhill from there. And it's around 500K daily price points, so it's not as much data for each one, but it can get us started. Basically, we will have kind of like this supporting tools. This is basically just a data loader that will load all of the cryptocurrency data sets in a pandas data frame and allows us to just like get the prices and whatnot. And as well as a manager that will allow us to just send all of this for kind of like distributed kind of like computing. And the code will be in my GitHub if you want to reach for it later. That is my GitHub, so feel free to check all the repos. I also have a more detailed deep learning talk that we did last November. And yeah, let's do this. Let's jump into it. So the first part is on just a brief intuition of machine learning. So can I have a show of hands? Who can say here that you have kind of like at least an intuition and understanding on machine learning? Cool, that's probably like around 80, 90%, so that's good. So we're just gonna rush through this. So imagine that, Crypto ML, they appeared in top tech magazines, they raised VC money with their initial prototype, their award-winning prototype, it did the job to predict quite accurately cryptocurrencies with just a random uniform multiplication. And now they need to figure out what machine learning is. It's funny because, and it's sad because it's kind of true. But to their finding, they saw that there's tutorials everywhere. And they found that, machine learning, in essence, is to try to find a function that is able to, predict data, an output based on a specific input. To give an example, we're going to use kind of like squares and triangles, as simple as it is, try to predict what shape it is. By visualizing it, if we imagine a two-dimensional plot where in the x-axis you have the area of the shape and in the y-axis you have the perimeter, you can see that in our feature space our shapes would be distributed. It's not accurate, but it would be distributed in a specific way, right? And this is what we would use kind of like as kind of like our feature space and our input into what we will want to create a function that allows us to fit this. And ultimately, machine learning is all about, finding the weights of the function itself. And in this case, you might see the common, f of x like equals mx plus b, where m and b are weights and biases. And we want to find a function that separates our data. Of course, in more complex examples, your feature space is not just, 2 dimensions of area and perimeter. It can be like hundreds and hundreds or even more of dimensions. And, the result basically will state, if it's a triangle or a square, i.e. if it's over the line, it's a square, if it's under, it's a triangle. The difference between the, old school if statement approach and machine learning is that you're able to let the model find the best kind of like fit. In this case, if we give it, an example square, an example triangle, it would try to say, well, the best fit is in here. We give it another example, it will try to find a better kind of like a better kind of like linear kind of like division, and then as it goes on and on, we try to kind of like find a better one. And this is done by minimizing a loss function. And as you can see, some use gradient descent, and you have kind of like a varied amount of different approaches to this. But it's ultimately, trying to optimize the weights for a specific kind of like function. When you find it, the difference is that instead of having something that needs to hold, real underlying information, and in some cases, IP of the data itself, in this case, you end up just with numbers, which represent the weights and the biases, which is really good, especially when you are kind of like an industry where you wouldn't be able to save every single permutation of a specific data set, mainly because number one, IP, and number two is just, infeasible, right? To be able to combine competitors' data into one single, massive if statement, it would be completely impossible. But ultimately here, we've succeeded. We found kind of like a line that divides those things. And if we give it a new shape, it finds, whether it's a triangle or a square. And now that we are machine learning experts, you guys can collect your certificates after the talk. They're valid in your LinkedIn profile, in non-tech meetups, parties, anytime you reply to a tweet. So at least that's what the crypto ML guys did. But in all seriousness, this kind of like function that we just saw, it is ultimately, synonymous to the single perception function in a neural network. So you have, the kind of like weights, mx plus b, and then your function, activation function, gets your output. The difference in neural networks is that you just take one neuron and you stack them up to be able to get a more flexible function, and you add more layers to what kind of like more flexible learning. And what would you do in more complex cases? The crypto ML guys ask themselves. Well, you just stack more layers, and that's the introduction to kind of like deep learning. And bear with me, like this is not just the case, but unfortunately, this has definitely become alchemy for some people, and that's not a great thing. Hence the disclaimer at the beginning that we don't use deep learning. We actually focus more on the feature spaces and the kind of like statistical models underneath. But ultimately, for the sake of hype, taking kind of like a very kind of like high level. Example, getting the classification of cats and dogs based on a multi-dimensional feature space where you're able to, with some dimensionality reduction, show domestication and size, and you're able to classify them, right? But then, now in practice, once the crypto MLs we're thinking, we're professionals now. You do come into a lot of kind of like challenges where a lot of the times you might have the right data set, but you might take the wrong approach. You might have the right approach, but you might have the wrong data set. You might not have cleaned the data well. So you need to think of ways that you can actually iterate and improve, which is not just getting more data. This could be extending our feature space, increasing the number of inputs, that could be. Regularization techniques like dropout, batch normalization, or normalizing data sets, and a whole host of other approaches. And then, the crypto ML guys ask themselves, can we use this thing for our, cryptocurrency price data? And the short answer is, of course not yet, because this is classification. This is not a sequential kind of like analysis. And instead of predicting two classes, we want to actually predict future steps. And this is when, sequential models come in. These are often used to predict, future data. It still uses kind of like the same underlying logic to find the weights and biases. But, you can use this in kind of like time-aware data sets. When it comes to the hello world of machine learning, there's arguments whether it is or it isn't machine learning, but yes, linear regression, in the kind of like most simple terms, it ultimately is. And kind of like implemented in Python, it's very simple, right? You import a specific linear model from scikit-learn. You take the prices, the times, you try to fit the model, find the linear function, and then you get a predicted set of predicted times for a window of say 10. And that works, right? So we're able to take kind of like the Bitcoin prices and be able to like run a prediction. But ultimately, this is very, very silly extrapolation, right? If we take this as kind of like as a basis, we would put that in by 2600, cryptocurrency is going to be the most valuable asset in the entire universe, right? And we basically want to find some more intelligent approach. Right, and the CryptoML team wants cutting-edge tech, right? Otherwise, they're not gonna, get featured in TechCrunch, right? And that's when deep recurrent neural networks come in. And deep recurrent neural networks are pretty much deep neural networks, but they're used to predict a future time step instead of predicting a specific class. So it's the same kind of like concept that you would have with linear regression. And with deep neural recurrent nets, they can hold more complex models. They can take more complex features in, and they can model more complex kind of like data sets. But ultimately, it's kind of like the same approach, just with a kind of like a more flexible learning algorithm. And let's recall kind of like the diagram that I showed for the neural networks. To visualize recurrent neural networks, let's imagine this and simplify it. So all of that, we're gonna squish it and see it as kind of like this linear thing. So that thing that we saw with all of the layers, we're just going to simplify it into this kind of like individual one node kind of representation. And the way that you would normally approach this is you would input kind of like your time series data into the neural network, and you would basically feed the last input, the last output of each neuron to the next iteration, as you see. So this is kind of like just unrolling the recurrent neural network on a time series data, but it's ultimately the same kind of like approach. To give an example with text, what you would want to do is you would want to train the model to predict the next character. So for the data set of Bob is, for B you would want to predict O, for O you would want to predict B, etc., 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 and you would just use your loss cost function based on whether it got the prediction right, and you do like the iteration on the gradient descent algorithm or relevant optimizer to be able to shift the weights so that it is able to find the internal representation it needs to be able to predict accurately, right? So ultimately for this, there's tons of different libraries that you can use for your deep learning crave. For this specific example, we jumped into just using Keras. And for training an RNN in Python, for the sake of simplicity, I built it in a very kind of like similar way of how we did our linear regression, to just show how, in essence, we are still doing the same. It's still trying to predict the next future steps, but the only difference is that you have a more complex model that can take, more that can build a more complex internal representation of the data itself, and can try to find the trends itself by just using the data. And of course, just using time series data more often than not is not enough. You might have to feed it many other things. This could be, some companies feed it articles, feed it even tweets, not just from sentiment, but also from keywords, and let kind of like the algorithms kind of like predict and understand the kind of like internal representations that is required. And yes, to build the LSTM, the RNN, the way that we would do, as you saw, we would need to just specify that we need certain number of nodes, certain number of layers, and this is what we're basically saying. We're using Keras, we're building a sequential model, and we just specify we're going to use this layer of LSTM with this number of layers. We're going to use dropout as a regularization, etc., and minimum square error to kind of like optimize and then return the model. But ultimately, it is still creating a model as we called it with the linear regression. By testing it, you would have the same approach, and you would get kind of like the same prediction. Maybe it's better, but ultimately to know, you would have to actually run some proper accuracy metrics on this. And now that CryptoML has VML, are we done then? Well, that is just the beginning, because ultimately just having a machine learning model is only the beginning to be able to make it available to people to use. And I'm aware there was a talk on Celery earlier today, so I think it's going to go quite well, as this will be just like a high level overview of this. So, when CryptoML was caught using deep learning, they were featured on the top 10, global news outlets. Their user base exploded. Now everybody wants to use them to predict the prices. They want to invest into BitConnect. They want to do all sorts of things, and they should have seen it coming, right? I mean, machine learning is known for being computationally heavy. I mean, that's obvious, but often it's forgotten how heavy, memory heavy it actually is. Especially as you start building more complex feature spaces, often you end up with tons of using tons of gigabytes of RAM in one single kind of instance. And I'm talking very heavy, holding whole models. And yes, you can break them down, but that requires kind of a lot of thinking and approach. And as any good startup, that's the thing that you don't have, right? And ultimately, you do have to take kind of a very pragmatic approach. You can't just keep, adding more RAM into your node or your cluster, because your instance, because they cost more, and then they become single point of failure. So you want to go, and it's a good time to go distributed, right? And there is a good library to do that. You guys saw that this morning. For the ones that didn't, there's this library called Celery. Celery is basically distributed asynchronous task queue for Python. And it actually uses Carrot internally to be able to interact with RabbitMQ, which is actually a really good set of names. But the way that it works is you would have a producer that gives tasks so that a set of workers can take them. And this is as simple as it sounds in order to implement. I mean, to implement well, it's another discussion, but actually just converting it into a Celery-enabled task, even if it's not even Django, if you just have vanilla Python, it's not hard at all. So we're gonna follow a simple step approach. Step 1 is take your code. Step 2, Celerize it. Step 3, make sure it works. And disclaimer, I haven't done that for this snippet, but ultimately this is the gist. Is basically just creating a Celery object that would connect to the queue, and basically specify that this specific task is it will be kind of Celery distributed. You need to make sure that the stuff that gets transferred across the network is serializable. So hence the util models that I added. But besides that, that is enough to just have a Celery worker. You run it, and it's just there listening to the queue, waiting for stuff. It is parallel, so it runs on multiple cores, as well as distributed, so you can run it across many instances that connect to the same queue. So as long as you have the queue address, you can just spin up many kind of workers. We're already halfway there. Now we just need to create the producer, and it follows the exact same receipt. You take your code, you Celerize it, and in this case, what we're basically doing is just, taking kind of a specific prices for all of the cryptocurrencies, and then just getting the predictions and then printing them. The only difference we do is that now that our prediction function is Celerized, instead of just running it, we run it with delay. Or with async. And then when we receive it, we just wait for it. Ultimately, of course, in a more complex architecture, you would want to make sure that it stores it in a database as opposed to just waiting for it to finish, because otherwise it's not very efficient. And yeah, and of course, step 3 is important. Make sure that it works. And then just once you run it, it basically is you have a set of workers listening for tasks, you have a set of producers, providing them, and ultimately, when it comes to balancing kind of a lot of load, it does make a significant difference. And it is not much more complex to run it locally than to run it kind of in a cluster. You can use this thing called Flower, which is a front end that allows you to visualize it, and it's pretty cool, very simple, but allows you to debug it. And you can just run it by connecting to the same queue, and it just listens to all of the stuff that it's doing. And we've won, right? We've made it distributed. So, we've surely just won the startup world. But, ultimately, once it comes that you have a distributed, architecture, now what you're doing is, you're actually spinning it up. You're spinning it up manually as in your kind of production environment. And that means that you may have, say, 10 workers, but you end up having some idle time and whatnot. And that is when you need to start thinking of your DevOps. And I think personally for me, DevOps is one of the most important things when it comes to machine learning. Ultimately, without a strong kind of like DevOps architecture to maintain and kind of like monitor and support your computation and your user base, you won't be able to get too far. So this is kind of like one of the most important things. And crypto ML didn't consider it. They remember the easy days when they didn't have tons and tons of like people just like throwing crap into the kind of like task and just sending tons and tons of requests. And their infrastructure, can't keep up. They probably have like a complete mess in their kind of like the way that people spin stuff up. They don't have awareness of what is running. They might have some nodes that actually run out of memory, etc., etc. And we underestimate often how complex the DevOps side is. It's complexity of staging and deploying machine learning models. What if it doesn't work? How do you revert it backwards compatibility of feature spaces or models? Distributing load across your infrastructure. So that like the size of the data doesn't clog a machine that is already using half of the RAM. Reducing kind of like idle time for instances. A node failure backup strategy so that if one fails, we can still pick up the task. Testing the machine learning functionality itself. How do you actually test the models? And then how do you monitor the ecosystem? How do you make sure that if something blows up, it's not your customer calling you at 2 a.m., but it's actually you just seeing this log info that goes like this shouldn't be there, and then you just jump in and fix it. And then it goes on and on and on. But ultimately the good thing is that there's tons of things similar to what we've seen that allow you to benefit from this. And Docker is an example. I mean, who here has used Docker in production, or just in their living room? Awesome. Yeah. Okay. Quite a lot. So basically, Docker is just a way of containerizing your applications. It's much more efficient than using a VM, and you can actually run multiple containers. And most importantly, I mean, I think for me, it's just the consistency across multiple environments. The fact that you can run it in multiple spaces, and you can expect the functionality to be the same without some crazy environmental nightmares, unless you screwed up. For which I can't say anything, but this gives you a lot of consistency, which is great, and it's also quite simple, right? So it's just as simple as creating a Docker file that specifies what do you need to do. Take the image of this guy that already created from CentOS a Conda enabled build. Take the repo, install the dependencies, and that's it, right? You've built it and you can run it. And ultimately, this allows you to be able to ensure that if it works in development, it should also work in other environments. And of course, it's not just about packaging everything into Docker, but it's making sure that Docker is just a thin layer on top of your actual application. So this could be done with pip or Conda, where you would be able to use the Conda install or the Conda or the pip install sort of kind of like interface. The obvious Docker Compose, allows you to just like spin up multiple containers, and this by itself would spin up RabbitMQ and the worker and the manager with everything set up for the containers to talk to each other. It sets up kind of like a network as well, and you can also scale it by just like turning it on, which is just so awesome. Right, I mean, if this was there years ago, we wouldn't have this daily Windows updates that have to go all the time, right? Because they would have built like a stable infrastructure. And then when you think about it, right, you have the containers. Now, how can you make sure that they are actually distributed across your infrastructure and that they're managed? And this is where Kubernetes and a few other things, but especially Kubernetes comes in, right? It is able to identify the nodes themselves that you have available and distribute what it calls pods across all of these nodes. And it would package up like things that need to talk to each other together, and it allows you to have much more flexibility, taking a much abstract and higher level approach into managing your infrastructure. But however, even though it is quite simple to use, which you probably can't see, it is still just YAML or JSON files that specify this Docker image with these configurations. Just package it up, put it there, open these ports, make them available, and that is it, right? And then the scaling is managed in large extent by kind of like this stuff. And there's a lot of stuff that you can use to support. So you can build kind of like with a local kind of like Kubernetes node in your Mac or in Linux. Then for production, you have different kind of like things like self-managed frameworks like in AWS, self-managed ecosystems, or alternatives that you can configure even more. And then there's also tools for you to benefit from that. And of course, right now the Mac Docker released Kubernetes enabled build, which is pretty awesome because now you can run everything and you don't need a mini kubelet for that either. And yes, so now that CryptoML has their entire stack ready, even though they're winning, still, it is just the beginning, right? Like you are just in the tip of the iceberg of the hype word sort of thing, right? Like your monitoring still needs to be enabled with, have things like Kibana. You can try to kind of like monitor. Like there's still too much things that you need to take into consideration. But at least you are in a nice place. You're in a nice position at least at this point in time. But for us, I think just to kind of like recap, we went through kind of like an intuitive understanding of kind of machine learning. We learned a bit of the caveats that are underestimated when taking this into industry, obtain some tips on building distributed architectures with Celery, and get a taste of Elastic DevOps. And I want you guys to, just use this very, very high level knowledge and dive into each one of the topics to just see what are all the options in actually making your machine learning kind of like reliable. The code again, will be uploaded into my Git repo, so you can jump in. Same with the slides, and do get in touch. I mean, if you have any further questions, that you don't get to answer right now, feel free to send me an email or add me on like whatever, Twitter, follow me. But yeah, so with that said, thank you very much, guys. I hope you enjoyed it, and I'll probably take some questions.